All right, the recorder is going. And let me double check, make sure it's actually recording. Yep, and that it is. I don't like the way they set up the projector because it's actually shining on my face. But you guys can watch that one, so you won't have me interfering with the screen. All right, so we're getting back to this one. All right, so this is really a history of. Ooh. Yep. Okay. So this is kind of a history of transistors and how technology has progressed from 1920s, from the not the 20s. It is the 20s to today. If you have not been to the Computer Museum in Santa Clara, you should go there. They have a mechanical computer on display right now, and that thing actually has a long history as well. So, for those of you who are kind of more mechanically inclined and like to see things click and turn, that's actually quite a piece to look at. They remanufactured this particular computer, mechanical computer, using the standards of when the computer was designed. In other words, they artificially introduced machine errors and tolerances, so that it's the same type of tolerances as when the design came out. So it was quite interesting. All right, but regardless of the technology, okay, this is the best part of computer science, is it is not really technology driven. Okay, so regardless of the technology or the size of the component inside a digital computer, most of the stuff inside the computer has not really changed over the past 40 years. Well, that's the interesting part. So with each component, each transistor, each vacuum tube, it is basically a valve or a switch. Each transistor has a source that connects to one of the two rails in an electrical system, a control signal as the input to determine whether the switch is going to be on or off, whether to allow the flow through or not, and an output that is connected to the said rail when the signal is on. Okay. In other words, it's just a switch. Okay. So just imagine a switch, like a normal electrical switch. It connects to the hot line. Okay. Goes through the load, which is the light or something else, and then connects to ground. So when you flip the switch, it completes the circuit, and electricity can flow through the device that you're turning on, and that's the purpose of a switch. A transistor is an electronic switch. What makes a transistor or vacuum tube different from a mechanical switch is the output of a transistor can be used as the control signal of another transistor. That is the most interesting part of transistors. Can anyone think of a electrical/mechanical device that has the same property? The output of one can be the input of the next one, but it's not a transistor. We have a lot of these components in cars. We still have a lot of cars with those components.
A starter?
Not a starter. The output of a starter is turning the crankshaft. It is not turning on another starter. What is the type of device? Go ahead. Fuel injector? No, because a fuel injector takes an electrical signal, but the output is the flow of fuel. So it's not going to be used to turn on another fuel injector. What is one component in a car where the output of one can be the input of the next one?
The battery?
You're getting close. It's not a battery.
Oh, the rotary.
Obviously, you guys don't have a whole lot of automotive failures because this is an item that fails quite often because of the mechanical aspect of this device. It's a relay. It's a relay. Okay. What is a relay? A relay is a switch. Okay. You can use it to close a circuit. You can put a load and have it to switch the circuit. But what is the input to a relay? Is there a little lever for you to flip? No. What is the input to a relay? It's an electrical signal. So it takes an electrical signal to control its state And then what is the output of a relay? An electrical signal that can be used to control another relay. Okay? So a relay can be used. You can make a computer out of relays. Now, it's going to click like there's no tomorrow. It's going to be really slow and really big, but you can do it. Okay? It can be done because it has all of the properties that we need in order to make a computer out of it. Okay? So these devices, including relays, if you want to make a relay-based computer, these devices can be networked in a way that can influence each other without much mechanical intervention. So nobody needs to flip a switch and stuff like that. And I mentioned here, for those who are curious about whether relays can be used to make computers, the answer is yes, but it will be very slow and not very reliable. Okay. And now we talk about two different types of valves, okay? Because we're talking about valves that can be used to control the flow of electricity. There are mainly two types. The first kind is a normal valve where the control signal, if the control signal is asserted, the output is also going to be asserting. And then the other one is negating. In other words, if the input is asserting, the output is not asserting. It's opposite. It is negated, okay? That's the only two kinds of there are only two kinds of valves like that. So what we'll do is I'm going to skip all this gibberish here. Instead, I'll show you a diagram of a circuit. Let me just zoom out a little bit so we can show the entire thing. So I'll briefly explain this circuit. You will not be asked to design circuits like this in this class, but this is actually very kind of important because each Q, okay, Q1, which is this device here, Q2, which is this device here, Q3, which is this device here, and Q4, which is this device here, each one is a discrete transistor. Okay? And the symbol basically means they are MOSFETs, metal oxide, what is it, semiconductor. FET is a field effect transistor. Okay? The technology is not important. What is important is how do we control, a particular transistor. When you the first two, Q1 and Q2, are of one particular type of transistor. The other two are of the other type of transistors. This is a P-type transistor. So Q1 and Q2 are what we call P-type transistors, and then the other two are called N-type transistors. What is the difference? Okay, they're all transistors. The only difference is to turn on a P-type transistor to allow electricity to flow through, you have to give it a low voltage. For a N-channel transistor, you have to give it a high voltage to turn it on. That's the difference. Okay, are we still doing okay so far?
What's the regulating mechanism to, like if it's high voltage went through a P, why wouldn't it turn on?
Because it will form a barrier. It will. Okay, the metal oxide is separating the gate from the actual substrate itself.
Okay.
But by putting a voltage on the gate, it will influence the material in the substrate. So it will turn the substrate material from neutral to N or P, and as a result of that, it can form a opposing PN junction. So electricity won't be able to flow through it.
Okay.
So that's why it's called a field effect transistor, because you're actually using an electrical field to influence the material to turn it from one type to another type. And with a PN junction, you can only let electricity flow through in one direction.
And so the material itself is altered when the voltage is high or low.
You're influencing what they call the holes and the electrons. So
Okay.
instead of having holes, it can have electrons, and therefore it will change the type of the material.
Okay.
But that's the device physics of these transistors. We are not interested in the device physics, in this class. There will be other classes that you can take that focus on only that. Okay. So what about the other stuff? What about T1 and T2 and T3? Those are terminals. T for terminal. So we have two terminals coming in. T1 is an input, T2 is an input. We have one output, which is T3. Okay. What about VCC and this little symbol down here? VCC is the supply voltage. It is a positive voltage. And this is the ground symbol. It is, you can look at it as 0 volt or the low voltage. Are we doing okay so far with the general concept of this circuit? Okay. All right, but what does it do? Well, just think about it. Think about how many, since we only have 2 inputs and they are independent. In other words, turning one input high does not influence the other input one way or another. How many possible combinations do we get?
For just the 2
We have 2 Boolean variable basically as input into this mechanism. How many combinations do I get out of true, false, or high, low values?
4.
We get 4 possible combinations. So we'll go ahead and take a look at each combination, and we'll see how each one can influence T3, which is the output of this little circuit here. Okay. So what I'll do is I'm going to start up a text editor on the side so we can let the picture stay here. And that works. Okay, that worked. So what we'll do, it will say T1 is low. We'll just use a 0 to mean low and a 1 to mean high. And T2 is also low. Okay. So what happens when T1 is low and T2 is low? So what we do is we follow the circuitry. Okay. These dots means there is a connection, and without a dot, these wires are just flying over each other. Are there any questions about reading that part of the schematic? Let me just point out using the mouse because this way it's recorded. When you see a dot at the intersection of 2 lines, it means there is a junction. Electrically speaking, they are connected. When you see a junction where there's not a dot, that means it's just a flyover. These 2 wires are not connected. So the vertical line and the horizontal line are not connected electrically speaking. Is that okay so far? So now let's go ahead and read this diagram and say, what happens when T1 is low and T2 is low? Well, T1 is connected to Q1, but remember with Q1, it is a P-channel MOSFET. It turns on when the input or the gate voltage is low. Same thing with Q2. Since T1 and T2 are both low, Q1 is on, Q2 is on as well. Is that okay? What about Q3 and Q4? Q3 and Q4 are N-channel MOSFETs. They turn on only if the input voltage is high. Since the input voltage is low, they are not on. In other words, this does not connect. This does not connect either. But this and this, they're both basically, you can just imagine this wire to be straight through because the transistor is on. Okay, so what do you think T3 is going to experience when both T1, Q1, and Q2 are on? Is it going to experience a high voltage, VCC, or is it experiencing a low voltage at ground?
Low.
High. It's going to experience a high voltage. Because T1 is going to turn on Q1. T2 is going to turn on Q2. So in other words, Q1 is completing this circuit here. Q2 is completing this circuit here. T3 connects to both. And as a result, it has quote-unquote 2 ways to connect to VCC, and that's why T3 is going to have the same voltage as VCC, which is a 1. Okay, it's a high voltage. Are we kind of doing okay so far with this? Yep.
What if both of the inputs are low? Then why would the output be high?
Because of the properties of the transistors. Because Q1 turns on when the gate voltage is low. Q2 also turns on when the gate voltage is low. But T1 and T2 connects to the gates of these 2, so both of these transistors are on. As a result, they complete the circuit to go to VCC. This one completes the path to VCC as well. Go ahead.
No, yeah, it's good.
Okay. Is that okay so far? Now, if you go to Fry's, okay, and you just say, I'm going to buy, some transistors and set it up like this, that's exactly what you will be seeing. You can actually design this experiment, use a breadboard, and and just design the circuit and actually get the same result. Okay, it will cost you, I don't know, maybe $20 or so, to get a breadboard, transistors, a voltmeter, and so on. But you can set it up and actually play with this. Okay, so let's take a look at the second combination. T1 is low, T2 is high. What about T3 in this case? Well, let's take a look. T1 is low. When T1 is low, Q1 is going to be on. Okay? In other words, T3 will find a way through Q1 to connect to VCC. Is that okay? Q2 connects to T2. It is high, so that means Q2 is going to be off. There's no connection here. Do I need both connections to get to VCC? No, because they are parallel circuits. So only one completion will connect the output to VCC. What about the other side? What about Q3 and Q4? Let's check on those things. Q3, which is this transistor here, connects to T1. T1 is low, right? When T1 is low, the gate voltage of Q3 is low. And because this is an N-channel MOSFET, a low voltage at the gate means the transistor is off. Okay? So this circuit is broken here already. What about Q4?
On.
Q4 is on. But remember, Q3 and Q4 are connected in series. They're not in parallel. That means if one is off, the whole thing is off. In other words, T3 cannot find a complete path all the way to ground. It can find one path to VCC. So what is T3? High or low? High. Okay. So the next combination is about the same. I'm just flipping T1 and T2. So I'm not going to explain this one because it really is the same reasoning except we flip the two. So T3 is going to be a 1. So the last combination is T1 is a low, high, T2 is a high, and the question is what is T3?
0.
It's 0, but let's find out why. T1 is high, so Q1 is up. T2 is high, Q2 is off. In other words, I cannot find a single path from T3 to VCC. Well, that simply means the signal is floating. It's not driven one way or another. So now we want to look at Q3 and Q4 and say, is it driven low? Do we have a path to go to ground? T1 is high, and a high voltage will turn on an N-channel MOSFET. T3 is on. It completes the circuit. Same thing applies to T2. It has a high voltage, and a high voltage at the gate of an N-channel MOSFET turns the MOSFET on. So T4 is on as well. This completes the circuit. This completes the circuit. Both switches on in series are now turned on. So now we have a path to go from T3 through to Q3 through Q4 to ground. And that's why T3 is going to be a low voltage this time. Yep, go ahead.
If T1 is high and T2 is low, when Q3 gets turned on, that voltage doesn't get transferred over to Q4, or how does that stop it?
Because one of these is off already.
But I mean, so if Q3 has a high voltage running through it, and then it's in series with Q4, why wouldn't Q4 have a high voltage running through it?
Well, Q4 will see a high voltage here because this connects. But Q4 itself is off. In other words, Q4 is not going to complete the circuit here because the gate voltage of Q4 is low.
Okay.
Because when you have two switches that are in series, they both have to be on in order to turn on the entire thing. Okay. Are we still doing okay so far with this picture? Okay. All right. So now we want to go back to C++ programming. I'm assuming all of you have the prerequisite of cisp310. Okay. Do you still remember logical operators? And or, and not, right? Ampersand, ampersand for and, double bar for or, and exclamation point for negation, not. Okay. If I give you T1 and T2 as variables, Boolean variables, and I want to use T3 to store the result of an expression, can you come up with an expression that can do exactly this? Okay. So let me just go ahead and try to do it here. Okay. In other words, what I'm asking is I want T3 this time not to refer to the circuit diagram, but I just want to use some T1, T2, and in between I have and or not and logical operators in between. Okay. Now obviously this is syntactically incorrect, but I just want to show you what type of operators we are talking about. Can you come up with an expression using only T1 and T2 so the T3 in this particular assignment operation will end up with the same result as the circuit itself?
T3 is not T1 and T2? Or
Yep.
not T1 and T2 is the...
Yep. Because all you have to do is to look at, oh, T3 is on whenever at least one of the two input is a 0. Okay, if at least one of the input is a 0, T3 is a 1. The only time T3 is a 0 is when both inputs are 1s. That sounds like a conjunction, right? Because conjunction says, if both things are blah, 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 that's the only time you get something. But it's the negation of that. So if I want to rewrite this, I mean, this is a little quick exercise. You can try to do it by yourself as well. Okay. If I give you this clue and ask you to fill in at the cursor, what type of operator I should put in here, what do you think I should put here?
Double and.
Do we use an or do we use an and?
Or.
Well, let's take a look. If you put an and here, does it fit the first set? 0 and 0 is 0. Not 0 is
1.
Well, non-zero, but in this case it's 1. Okay, so the first case works out. Second case, 0 and 1 is 0. Not 0 is 1. Works out for the second case. What about the third case? Well, that's just a flip of the first one, of the second one. So we'll just say it works. What about the last one? 1 and 1 is 1. Not 1 is 0. It works out for all 4 cases.
And that's it. And the true and false is false because of the logic gates we learned a while ago.
Say again?
You said true and false is equal to false.
True and false is false, right?
Okay.
And 1 is representing true, 0 is representing false. Yep. All right. Is that significant? I just hooked up a whole bunch of 4 transistors. And what is the result of hooking up these 4 transistors in this particular way? I now have a logical expression. It has the same result as a logical expression. There is a particular name to this logical expression. The name of this logical expression is it is a NAND, and in fact I'll do it NAND 2 because it has 2 inputs. So it's a NAND 2 of T1 and T2. It's a negated AND gate. Right? So using only 4 transistors, I can make a single NAND gate out of it. Well, but why not an AND gate? Why not an OR gate? Why not do something that we are used to? Why a negated AND gate? Well, because it's easy to make, okay, using N channel and P channel MOSFETs. But is that really going to be useful? I mean, So let's move on. Okay, so I just did this part here. It's in the notes, but I just did it. So how useful is a NAND gate? And let me just kind of flip back to, I just lost my, okay, there we go. All right, how useful is a NAND 2 gate, 2 input NAND gate? Can I use NAND gates to make up something that we are familiar with, like a regular AND gate, a regular NOT gate, and a regular OR gate? Can we do something like that? Okay, let's take a look. Well, the first thing we'll do is we'll take a look at the representation of a NAND gate. This is a NAND gate. Okay, if you just focus on this part here, that's a NAND gate. The little bubble means negation. It's negating the output of something. when you see this shape with a straight edge on one side and a bullet on the other side, this is an AND gate. So the negated AND gate is a NAND gate. Okay? This is how we can do a regular this is how we do a non-negated disjunction. This is just negation, excuse me. This is just negation. What is negation? What is the not or the exclamation point in C++?
It's not.
It's just negation, right? You know, not 0 is 1, not 1 is 0. That's how we do it. All you have to do is to hook up the input to both of the inputs to a NAND 2 gate. That's all you need.
So why are we making the inputs no longer independent? Because we had two terminals you said that were independent, but now we're not.
That's correct, because I want to make everything out of a NAND 2 gate.
Okay.
And that's how you deal with a negation, just a simple negation. The next one here is a OR. Okay, so if you look at this picture here, that's an OR gate. So an OR gate is a little bit complex because I need to use 3 NAND 2 gates to make an OR out of it. And this is the equation to do it. A or B, okay, this symbol looks like a B. That's how we write OR in mathematics. Okay, A or B is the double negation of A or B, because double negation cancels each other out. Is that okay? But when you have a negation, hello.
Can I get some help? You have an assistant?
I'm having a class right now.
Yeah.
I do not have an assistant with
Be
me.
a class, but I was supposed to be at 8:30 this morning.
Okay.
I have him, yesterday was his first day of school, today's got doctor's appointments.
Okay, I cannot help with that part, but I can tell you where the classroom is.
This is it. Started at 8:30 this morning.
Okay. So
28?
what you need to do is to contact the instructor.
Yeah, that's who I was trying to find.
His office is in room 133, which is the next aisle over. There's a glass door, and if you walk through the glass door, you can ask the person behind the desk.
Outstanding. Thank you so much. Have a good day.
All right. Okay. Getting back to the equation here. Okay, so this is double negation. So when you see a single negation, and then inside you have an OR, you can apply what we call De Morgan's law. Okay, De Morgan's law can turn a OR with an outer negation into the negation of the individual component in a conjunction. In other words, this component, this part here, turns into this. Is that okay? Maybe?
Yes. Can you show that?
Okay, let me just see if I can highlight it. I think I can. Okay. This part, which is the negation of an OR, turns into this part here, which is a conjunction of the negated individual component. That's called De Morgan's law. Okay? And once we have this, we already know how to negate a component using this trick here. That's what we apply here. But when you look at this negation of the conjunction, hey, that's just NAND. So that's why we have a single NAND here. So using 3 NAND 2 gates, we can implement a regular logical OR. Is that okay so far? Okay. And the last one is a non-negated conjunction. This is actually a typo here. This is a non-negated conjunction, and that's a disjunction. I had to fix my notes. But this one is this just a regular OR. Okay, great. So now we can use transistors, individual transistors, to make logic gates. And we can get back to all the usual logical operators that we are used to. Just an OR, an AND, and negation. Are we still doing okay so far? Okay? More or less? Okay. Okay, I'm going to skip the logical versus the digital part, and then I'll skip all the way to values, numbers, and representation of numbers. Okay, so I'm going to ask you this question. What is this symbol?
7.
It's a vertical line followed by a slanted line, right?
Yes.
But what does it mean?
It represents the value.
The most common understanding is it represents the value 7. But what exactly is 7? Okay, when you hear the word 7, okay, it's just sound wave, right? It's just a variation, the change of air pressure. Okay, that's physically what 7 is. This is just visually what 7 is. But what exactly is 7? What is the meaning of 7? How many samurais are here? 7. There's 7 samurais. So 7 is a value. Okay, the value of 7, the number of samurais in that picture, and by the name that's anime, is called
Naruto.
7 samurais. So it's a concept. Okay, 7 is a concept. It's a quantity. Then what is this?
The symbol for it.
Is a symbol to represent that quantity. For those of you who know Chinese, what do you think this is? No,
I guess it'd be
it's 7. It's the character that means 7. Okay?
It's like an upside down 7.
Hmm?
It's like an upside down 7.
Upside down 7?
Yeah. Because usually
You
you
mean
write
this
7.
part here, or you mean those people put a stroke there?
Yeah, yeah.
Okay, so if you have your, I can see people with different native tongue here. So you have your own word to represent the same quantity. Are we still doing okay so far? Are we separating the concept of the actual quantity from the words that we use to convey that particular quantity to another person? Is that okay? If you're all by yourself your entire life, would you need a word to represent a particular quantity?
No.
Because you're not communicating with somebody else. Okay? You can come up with your own representation so that you can remember, oh, last time I got attacked by 7 wolves or something like that, right? Okay. And it's the same thing here. It's just a picture of a particular facial expression, and then I put here all the different ways to express that expression in different languages. It's the same thing. Okay. So now we move on to base conversion. Okay. There's a lot of details here, but it's not really that important. So forget about the details. What I'm going to do is to ask you guys, how many people feel that you are competent enough to work at McDonald's? So that if the machine tells you that you have to make change for $27.93, okay, you know how to use the least number of coins and bills to come up with that amount. How many people feel confident? Okay, it may not be quick, okay, but you can do it, right? Okay, so let's just look at that amount. So this is going to be fun. Okay, so we are going to take a look at exactly that amount, $27.93. Okay, there we go. And by the way, this is a number. It's a representation of a quantity. The actual quantity is 2,793 pennies. That's one way to come up with that amount. Not usually preferred, but that's one way to do it. Okay? So tell me how you convert this into the least number of bills and coins. And I'm just talking about the main ones in circulation, not the odd ones. Okay? So tell me how you do it.
A 20, a 5, 2 1, 7, or 3 3/4, 2 dime, 1 dime, 1 nickel, and 3 pennies.
And you did not even break a sweat. Cool. Okay. Is everybody kind of feeling comfortable with that conversion? Yeah? Well, you know more than what you need to do base conversion already. Really? Base conversion. Okay, so let's take a look at the denomination of currency here. Okay, so in the US, we have pennies, we have nickels, dimes, quarters, $1 bills. I know we have half-dollar coins, but they're not in circulation a whole lot. I know we have $2 bills, but most people do not have those, so we'll skip to 5. We have 10s, and then we have 20s. So just for this particular example, do you see a repeating pattern with these denominations? From 1 to 5 is a times 5, times 2, times 2.5, times 4, times 5, times 2, times 2. Is there any type of repetition, any pattern that you recognize? There's absolutely no pattern. This is crazy. Right?
Yes.
And yet, you can deal with it. So what if I'm to tell you something that is regular, that has a regular pattern to it? Does it make it easier? Okay, so let's go ahead and change all this stuff here. I know some of you have taken this class before or another class where I talk about base conversion. I'm changing the way I do it, okay? So this is new. This is going to be more exciting. So instead of counting in dollars, we'll be counting in pennies. So this way we can deal with all the single penny stuff. So now we have a penny, we have a 2 penny, we have a 4 penny, we have a 8 penny, 16, 32, 64, $1.28, $2.56, and next one up is $5.12, $10.24, and $20.48. That's all we need, I think. Okay. So now we change the crazy currency system that we already have into something that is making a whole lot more sense. No pun intended. Okay? More sense. Okay. So using this really odd currency system, can you come up with that same amount of money?
Not as quickly, but yes.
The answer is quicker. Okay, so let's figure out the answer to this one. Okay, so we have an amount of $27.93. Okay, and how do you approach this problem? This is the amount that I want, and those are the currencies, and those are the bills and coins that I have. So how do you work this out?
Track the largest that would fit.
Look at the largest one first, right? Do you have to do any division like normal, currency stuff?
No.
No, you just compare, right? Is 27.93 greater than or equal to $20.48? Yes. We'll take one of those. Okay? So you say, yep, we need one of those. So what is the difference? What is left over?
$7.45.
$7.45. Okay. So you look at $7.45. Do I even want to look at 1024? No, because it's 1024 is more than 745, so we don't even need to consider it. So the next one down is 512. Okay, so we'll take one of those, 512, and we have 233, right? No, yeah, 233. So you look at 233, and you say, well, we're going to skip 256. Okay, we'll go straight to 128. So 128, let's get one of those. And we get 105 left. We look at 105, and what is the next one down?
64.
We get one of the 64s, and we get
41.
41. Yep. And then look at 41. We'll take a 32. And then we have 9 cents left. We look at 9 cents, we'll take a 8 cent. We have 1 left. And then we have 1. We take 1, and we're done. Okay? But what is the number? Right? Well, the number is we have one of this, 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 and one of that. That's binary. Because we either have one or none of each value. Okay? And that's the basis of base conversion. Okay? That's basically base conversion. Now, in the example, I use a slightly different system, but basically it's the same concept. Yep.
But most people,
Mm-hmm.
even computer science people like yourself, deal with money every day. So for you to come up, or someone else to come up with the amount of bills needed for $27.93 is most likely second nature for most people. This binary step, fewer steps, yes, but you still need, there's more,
You need
more
to
thought needed.
Yes,
to
but
produce it.
but that's only because we were trained with the other currency system. Doesn't mean it's actually natively easier. Okay, I'll present another argument to push the agenda of binary is better. Okay, multiplication table. For those of you with kids, okay, in their maybe third grade or so, you probably will understand. Oh man, the multiplication table. Okay, but just remember when you were a kid. Okay. How do you know 6 times 7 is 42?
Memorize it.
You have to memorize it, right? There's no really other way to do it. How do you know 13 minus 7 is 6? That's memorization as well. Okay? And we have all of these rules to remember, to memorize. Okay? How big is the multiplication table? The entire table is 10 by 10. Because you have 0 to 9 on one axis and you have 0 to 9 on the other axis. So fully populated, the table is 10 by 10, which is 100 items. Then you'll say, well, yeah, but out of the 100 items, a lot of these items are not needed because 0 times whatever is 0. Okay, that cross out one row and one column. And then you say, oh, but there's also 1, okay, 1 times whatever is whatever. Fine, cross out another row and another column. So now we only have 8 by 8. Okay? Out of the 8 by 8 left, you say it's symmetric because 4 times 3 is the same thing as 3 times 4. Okay, chop it in half. 8 times 8 divided by 2 is still 32 items. All right? So the multiplication table it takes about a year, or at least half a year, for third graders to memorize the multiplication table reliably. Okay, now you can tell me, a more accurate estimate if you have someone who's taking third grade at this time. But I think it takes about half a year, And then addition is the same way. How do you know 2 plus 9 is 1 with a carry? That's memorization. It really is. Okay, so we have all of these rules. Okay, we have one table for addition. We have one table for subtraction, and then we have another table for multiplication. And only then, okay, only once we have mastered all 3 tables, we can address division. Right? Because when you look at division, you have to be able to do multiplication by heart before you can do division in base 10. Is that making any sense? Are we all set up to push the agenda for binary? Okay?
The Egyptians used binary for multiplication and division.
And it makes sense. What is the multiplication table of a binary system where you only have zeros and ones? The table only has 2 rows and 2 columns, right? Because you only have to deal with 0 and 1 and 0 and 1. What is 0 times 0? 0 times 1? 1 times 0? 1 times 1? You got the whole table. Do you think a third grader can get this in a week?
Yes.
Let's deal with subtraction. What is 1 minus 0?
1.
What is 0 minus 0?
0.
What is 1 minus 1?
0.
And the only one that's tricky is what is 0 minus 1, right? Well, but that's the same question as what is 0 minus 5 in base 10. You have to borrow. That's it, okay? So you basically say 0 minus 1 is 1 with a borrow, because the next digit is going to be twice as much as this digit here. But it's the same concept as borrow. How long do you think a third grader needs to memorize that table? Another week? Addition. 0 plus 0.
0.
0 plus 1.
1.
1 plus 0.
1.
1 plus 1. That's the only one that's tricky, because there's no 2 in binary. It'll be a 0 with a carry. It's just like 5 plus 5 in base 10 is a 0 with a carry. So the next digit now has a 1 to begin with, right? And how long do you think it will take to memorize that? At the most another week, right? So 3 weeks we are done with multiplication table, division, subtraction, and addition. What about division? Division has got to be hard with binary, right? Has got to be a nightmare to do that. So we'll go ahead and, I'm going to turn on the lights so I can use the whiteboard to illustrate this. All of this will come back, okay? So I'm just giving you a fast forward to stuff that we'll be talking about later on. But this is going to be interesting. So we'll look at division. Now division is really a nasty thing if you're dealing with base 10. Okay? Because you have to really do multiplication by heart to be able to do this quickly. Okay? So we move, okay, 3030 doesn't have a 4501, so the only one, we can start here. How many 4501 do we have in 30,304? How do you know that?
I went through 9, 8.
You kind of do the guesstimation, right?
Yes.
Yep. So 7 of these, right? And then you have to do, okay, 7 is, that's the easy one, that's the easy one. 7 times 5 is 35, and they put a 3 here, and then 7 times 4, oh, that doesn't work out.
It doesn't work out.
Dope. It's only 6.
Yes.
That's base 10. I hate base 10. Let's try binary. Okay, that's pretty long. And we'll use, okay, tell me what you want to use as a divisor. Give me something that's not trivial. 5 digits, 6 digits, I don't care.
11010.
Okay, say again.
11010.
Like that. Okay. We take this, right? Nope, 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 yes. I don't have to know division at all to do division. I only have to be able to what? Compare. Okay? Is this bigger than the other one? Okay, fine. Let's do division here. Okay, so we have 1, 1, 0, 1, 0. Okay? Now we have to do binary subtraction. That's an easy one. 1 minus 1, that's another easy one. 0 minus 0, another easy one. 1 minus 1, easy. Only one that's tricky is this one. 0 minus 1 is a 1 with a borrow. So 1 with a borrow. Then we have 1 minus 1 again, that's a 0. Done. Take the next one down. The 1 here. This is a tricky one because it's a 1 with a borrow, right? So now we have a borrow, okay? And then, but once we subtract 1 from 0, we have a 1. 1 minus 1 is 0. And then 1 minus 1, this borrow is coming from this column. That's also a 0. So we have 1, 0, 0, 0 left. Are we doing okay so far? Sort of? Okay. We take another digit down here. Not enough to make a difference. Put another one down here. Now we can do something. So we have 1 again. Will I ever have more than 1 here?
No.
No. It's either 0 or 1. So there's no division involved. There's no multiplication involved. Well, there is multiplication involved because we are multiplying something, the divisor, either by a 0 or 1. Is that difficult?
No.
No. Multiplication by 0 is a 0. Multiplication by 1 is just the divisor itself, right? Okay, so now we do it again. And we have 1 here, 1 with a borrow. 0 minus 0 is a 0. 0 minus 1 is a 1 with a borrow. 0 minus 1 is a 1 with a borrow. 1 minus 1 is a 0. 0 minus 1 is a 1 with a borrow. 1 minus 1 is a 0. 1 minus 1 is a 0. We're done. Okay? So we will get to this later on in details. So if you don't get it this time, don't worry. We will get to this later on. Okay? But I'm just kind of showing you the steps. Do you see, if you were trained to do everything in binary from 3rd grade, from 2nd grade, this would be easy. Okay? You can do it just like that. Does that make any sense? So I think we should change from base 10 to base 2 from kindergarten. What is the only downside of binary numbers?
More work,
More digits.
more digits.
A lot more digits. Okay? So we have a pretty long number here, so it will be kind of hard to spell it out or to communicate, like in a newspaper. If I want to express the national deficit at this point, it's going to be like, it'll take up half a page. Okay? But we have a solution to that as well. What is it? Hexadecimal numbers. Base 10 numbers. Base 16 numbers, sorry. Okay? So if I were to turn this number, which is in binary, into hexadecimal, now hexadecimal is base 16 because hexa is 6, deci is 10, so hexadeci is base 16. Base 16 is basically chopping a number into blocks of 4 bits. And then each block has a hexadecimal digit. 1010 is A because it is actually the quantity of 10. 1100 is C, it is the quantity of 12. 1010 again, which is an A, and 10111 is 7. So if I were to rewrite this binary number in hexadecimal, it's AC7. Did I do any multiplication? Did I do any division? Did I do any subtraction? None of that stuff, right? All I did is to look up the bit pattern and go, oh, this bit pattern corresponds to that hexadecimal digit.
But you memorized. So you memorize 1010 is equivalent to A.
Correct. The entire table goes like this. So all zeros is a 0. 1, 2, and there are 16 of these all the way down to the last one, which is 1111, and that's an F. So there are 16 entries. How long would a 3rd grader take to memorize that table? Another week. It's easy. Okay, to do it quickly, yeah, you need practice, but the table has no tricks to it. It really is just looking up, and that's the answer.
Why does it stop at a block of 4, not a block of 5? Because a block of 5 would be 2 to the 4, which is 16, right?
Well, we stopped because we don't want to borrow that many letters from the alphabet. Plus, 4 is a power of 2 too, so that makes it kind of handy. All right. Does anyone here do any type of networking stuff? No. Does anyone know what is an IP address? Sort of. Okay. And how do you spell out an IP address using IPv4? The usual way to do it.
I just know how to get the IP address.
Okay. Give me one example of an IP address.
165.158.0.1.
Okay. And can each component exceed 255?
No.
Nope, because each one is a byte. How about IPv6, version 6 of IP, the Internet Protocol? Do they use decimal numbers in IPv6? What kind of numbers do they use in IPv6 to denote IP addresses? Hexadecimal numbers. Okay, so all of this stuff, I will explain all of these in more details later on, but it's really important because it's not really just for programming, it's also for other types of work related to computers. Yep, go ahead.
So there's octal groups of 8 then?
Yes, octals will be groups of 8, and that's kind of the older standard. People in the past, do a lot of octal numbers, but we don't really do that a whole lot anymore. So the octal table is going to be 0, 0, 0 mapping to a single 0. 0, 0, 1 is 1, 0, 1, 0 is 2, and the last one is 1, 1, 1, which is a 7. And C can deal with octal numbers as well as hexadecimal numbers.
How come it doesn't use those? It just aren't those bytes?
Because it doesn't align with a byte, okay? How many octal numbers it will take to represent a byte, which is 8 bits? It will be 2 octal numbers and 2/3, right? But it will take exactly 2 hexadecimal numbers. And that's why hexadecimal numbers are nice, because they line up with byte boundaries. Question, go ahead.
What's so important about a byte? Byte is 4 in a byte.
A byte has 8 bits.
Because of convention?
Okay, I think I know why it is significant. Okay, imagine you have a typewriter. Okay, just a regular typewriter. How many different symbols, letters, and digits usually is on the typewriter? Well, let's just count the basic ones. Okay, so you have lowercase a to z. I'm talking about a typewriter in English. Okay, so you have a to z in lowercase and then a to z in uppercase. So that accounts for what, 52 things that you have to be able to type. And then you have the digits, 0 to 9, right? So now we have 62 things that you have to be able to type. But then we also have punctuations, okay? Period, comma, semicolon, colon, quote, double quote, parentheses, all the usual stuff, right? So let's say there are around 20-ish of those symbols that we want to put on the typewriter. So now we go from 62 to about 80 something. Is that making any sense? Okay. So it will take, how many bits do you need in order to have a bit pattern that can differentiate one thing that you can type out of a typewriter from the next one? It will take 7 bits, okay? And that's why a lot of telecom equipment in the early days, they only use 7 data bits, because that's all they need in order to print something. If you want to print out a letter from a tape or some other storage device, you only need 7 bits. But they bump it up to 8 bits later on because it's just a round number. It's a power of 2. And it's just, it's not that much more expensive, it's just 1 more bit, but it does make everything kind of round off a little bit better. So that's why, a byte has 8 bits.
And why did you say the keyboard only needed 7 bits?
Huh?
Why did you say the keyboard only needed 7 bits?
Because there are less than 128 things that we normally want to type on the regular typewriter.
Okay.
If you look at the ASCII table, it only goes up to 127. It does not go to 255. So out of the ASCII table, we only use 1/2 of the values that we can possibly use out of a byte. But a byte has 8 bits because it just lines up better. Any other questions? Other questions? I'm going to turn off the light and just finish the last bit of the lecture material, and I'll tell you guys what you need to read, and I'll give you a little preview of what we'll be doing on Thursday. All right. So this slide is pretty much done by the time we get to base conversion, when we're done with base conversion. And that's low-level mechanisms and representation. So what we'll do in this class is we'll kind of go through, this is just a link to the LogicSim webpage. There's not a whole lot to do. We will talk about binary numbers, addition and subtraction. So you want to read that particular slide as much as you can before we meet on Thursday. And there are some lab activities here. So there's one for LogicSim, and also the other one is to set up a Linux environment to do your homework. That one might take you some time, but it's not set up yet, so don't do that one just yet, okay? But what we'll do is the first part of this semester, we'll be using this program called LogicSim. It's a Java program, so you can get it running in Windows, in Mac OS X, or in Linux, okay? It's operating system independent. It's a really cool software. On one side, it allows you to make circuits by just dragging and dropping, okay? On the other hand, it will also allow you to simulate the circuit. In other words, I want to see what happens when I give a high value here, a low value here. What is the output of this mechanism? It can simulate. Okay, so it's really a cool little program, and we'll be using it for maybe about half of this semester. We'll be making a processor. Okay, we'll be making a processor out of Logic Sim. I'm going to do most of the work, but you guys will play with it and make modifications to the processor. This is for the second half of this class. Okay, we'll be using Linux as an environment to run the tools that we need to write programs in assembly language. This is kind of a cool little tool because it is very portable. It is a single zip file that you expand into a folder. But you can expand into a folder on a thumb drive. You plug in that thumb drive onto any machine running Windows. You double click on the batch file and you start with the virtual machine. The virtual machine has Linux already installed, and you'll be doing your homework assignment in that particular virtual machine. Yep.
Which distribution are you using?
I'm using Debian, so this is a Debian distribution. If you already have a native Linux environment, you probably can use it, but it has to be a 32-bit environment. And most people have a 64-bit. There's a batch file, there's a shell file to start up a QEMU for Linux systems as well. So you can actually run QEMU inside a 64-bit Linux system and just use it just like everybody else. So it's set up for major distributions of operating systems, except for Mac OS 10. Okay? So go ahead and read. So your job, your reading assignment, is going to be binary numbers, addition, and subtraction. That's what the lecture is going to go over. And then the lab for Thursday is going to cover how to set up a Linux environment for homework. So that's the plan for Thursday. Are there any questions? Yes, go ahead.
So nothing
Nothing to turn in.
for us to turn in before Thursday.
Nothing to turn in, but there's reading assignment, and also just go to the Logic Sim website, download the program, and make sure you can run it on your computer. It's just a jar file. Double click on the jar file and it will run.
Okay.
All right, so that's it for today. I will upload the lecture and this portion later on today, and I'll see you guys on Thursday.
And how do I add this class on my Moodle?
In Moodle,
Yeah.
the enrollment password is ASM.
ASM?
Yep.
Okay, and then, so when I log into Moodle, how do I